Okay, guys, I'm sorry I'm not there today. My husband had surgery yesterday, and I needed to stay with him for another day while he's recovering. So I've got your notes recorded. That's these. You just need to listen to what I'm talking about and use what you learned here to solve some problems. What we're looking at basically here are some of the building blocks that we're going to need to actually be able to do physics itself. This is not necessarily physics. These are the things that we use while we're doing physics. Okay, so two of the big words we're looking at here first. Yeah. Is qualitative versus quantitative. All right, where was I? Qualitative versus quantitative. This is a big deal in physics. What do we mean when we say qualitative? What we're looking at for qualitative is we are going to be applying knowledge to write, basically. In other words, what are we talking about here when we're writing? Writing, we are talking about, we are going to be describing. We are going to be explaining. So describe, explain, compare, or predict. But it's using words. It's not math-based, it's concept-based, okay? Versus quantitative, which I bet you can guess is applying math. It is math-based. In other words, but it's a specific type of math. We're going to be, and we're going to start from a fundamental equation and apply algebra. Okay? Now, how do we represent information in physics? There's 4 main ways we are going to represent information in physics. We're going to start with equations. We could use words. And of course, equations is quantitative, words are quantitative. But we also have graphs and diagrams. Now, the cool thing about graphs and diagrams is those sort of bridge the gap between equations and words. In other words, between qualitative and quantitative. All right? So now, it says, in this example, it says an AP Physics problem requires that students be able to justify the use of a mathematical equation to solve a problem. How do we justify that, the use of it? A carpenter might use screws and screwdrivers or nails and a hammer to join 2 boards. In your own words, describe how the carpenter's selection of the correct combination of fasteners and tool is similar to the requirements that you be able to select and justify the correct data and mathematical equations. I want you to think about that. If he chooses screws and a hammer, is he going to get that far? No. If he chooses nails and a screwdriver, is he going to get that far? No. So you have to have the correct combination of both the tool and the actual fastener itself. You have to have the things that go together. In other words, you can't just do words if you don't understand, you have the right concepts that you're talking about. You also can't solve a problem if, quantitatively, if you don't start with the right law that describes the situation. The algebra doesn't mean anything if you don't have the right equation, fundamental equation to start with. Does that make sense? I want you to kind of take and summarize what we just talked about here. Okay? So now, what is the strategy for solving problems in physics? The first one is set up the problem. What do I mean by that? In other words, read it and figure out. This means figuring out what the problem's asking for. How can you solve something if you don't even know what you're solving for? In other words, what are the relevant concepts? Are we talking about momentum? Are we talking about energy? We don't know. And along with those relevant concepts, what representation should we use? In other words, are we going to use a diagram? Are we going to use a graph? Are we going to use words, equations? We don't know. We've got to figure that out and set the problem up before we know what to do. So you're going to have to know concepts, and you're going to have to think representations of those concepts. So now, after that, what we're looking at is solving for the desired quantities. Now, solving doesn't always mean mathematically, okay? This is the quant-qual part, okay? This is where you take your either concepts and talk about them and how they relate to the problem, or you take your fundamental equation and you do your algebra. So we're going to use those to describe, justify, explain, or predict. Now you see why I had to use those to do that word sort today, right? So this is the big quant-qual part. Right? Now, what do we do after we solve? This is where we have to decide whether or not our answer really is right. So we're going to reflect on the answer. In other words, did we support? In other words, this means supporting your claim with evidence. In other words, did you find the evidence you thought you would? Did you show that it was indeed something, or it wasn't something after all? Okay, so supporting your claims with evidence, and assessing the reasonableness of your results or solutions. So you came up with some number. Is that number correct? Is it even within the ballpark? If you're looking at something you can pick up and you come to the conclusion when you solve that it's 3,000 pounds, you know you can't pick up 3,000 pounds. That's not reasonable. So you've got to sometimes look at the reasonableness of your results or solutions. Do they make sense? And then finally, the last one is extend. So this means considering effects of change on the problem. And they do this to you a lot. They'll give you a problem and then they'll suddenly stop and say, so, what if we change this? What would the result be then? That would be an extend. So considering the effect of changes in the problem. you've got to know how to do all of those things. All right, so now, explain why you would not entrust the construction of a new home to an architect who only had a mental model of the plans. It's all in his head, nothing's written down. In your own words, connect this expectation to the use of a drawing in the solution of a physical problem. What do we know about construction of a new home? We know it has to be specific and follow very specific rules or guidelines, okay? And very specific measurements. Well, if it's all in your head, how do you do that? You have to make a blueprint so somebody else can follow your model. Well, guys, this is the thing that, this is the same purpose that a diagram or a drawing in a solution to a physics problem gives. It allows somebody else to follow your line of logic, also for you to figure out whether or not it's a good place to start. If we're dealing with forces, of course, the first thing we're going to do is draw a diagram of which way all the forces are acting. In other words, which ones are important to our problem. Drawing a diagram helps to clear things up. In other words, how pieces of a problem work together. So now we have the system model versus an object model, and you're going to hear me talk about this. Most of the time in physics, we deal with object models. In other words, we treat it like a point mass. Well, when can we do this? This is when we ignore its size, its shape, okay, and internal structure. Okay? In other words, all points on the system move together. In the same way. However, the system particle, we can't ignore internal structure. Okay? What does this mean? What it means is that usually it's a complex system, and that it is usually an object spinning or the shape changes. So now it says object model or system model. Is an object model or system model right for the words in bold? Justify your choice. All right, the description of the motion of the Earth, just the Earth. Well, if you think of the Earth does spin, but all of the points on the Earth spin the exact same way, at the exact same time. So guess what? This is an object system. An explanation for the motion of the Earth as it orbits the sun. Well, the sun sits still and the Earth moves, so they're not moving all at the same time. So this is a case where it's a little more complex. In other words, something is spinning around something else. So this is a system. Description of the motion of a girl on a bike coasting down a hill towards an intersection. Okay, so the girl on the bike is moving all together. She and the bike are all coasting right down the hill. She's not pedaling or anything. She's just coasting. So this is an example of a, object. All of her is going down the hill at the same time. The mass of water in a goldfish bowl, assuming the shape of the bowl. Again, this is everything, all of the water doing the same thing. So it is an object. However, water poured into a goldfish bowl. That falls under it changes shape. So this would be a system. Ice skater gliding in a line across the ice. All of her is going across the ice the same way. So this is an object. However, an ice skater spinning in place on the ice. She's not all moving. She's spinning now. Okay? So this makes her sometimes a system. All right, so let's look at standard SI units, units we use in physics. Time is seconds. Length is in meters. Mass is in kilograms. Temperature is in Celsius. That's big C. Electric current is in amperes. That's big A. Amount of a substance is in moles. This is MOL. And luminous intensity is in candles. Okay, mass versus weight. These are two very different things. Mass is simply how much of something there is. In other words, the amount of a material. Okay, versus weight, which is how strongly, your weight is what you measure on the scale. Your mass never changes, but your weight can. Your weight is your mass dependent on the gravity. In other words, how hard gravity pulls on an object. In other words, the more gravity you have, the heavier something is, heavier something weighs, even if it has the same mass. You weigh more on Earth than you do the moon, because the moon has less gravity. Point. Okay. Conversion units in physics. 1 minute is what? 60 seconds. 1 hour is 60 minutes, which is 3,600 seconds. 1 day is 24 hours. An hour is 3,600 minutes. A minute is 60 seconds. You end up with 86,400 seconds in a day. 1 millimeter is 0.001 meters. In other words, 10 to the negative third meters. 1 centimeter is 0.01 meters, which is 10 to the negative second meters. A kilometer is actually 1,000 meters, which would be 10 to the third meters. 1 inch is 2.54 centimeters. 1 foot is 0.3048 meters, and 1 mile is 1.609 meters. We're going to use all of these to do conversions. Unit conversions is a big thing here in physics. They're helpful. So what are some of the things we know? Going by factors of 10, 10 to the negative 15, then we go to 10 to the negative 12, 10 to the negative 9, negative 6, negative 3, and then we go to the negative 2, negative 1, then 10 to the first, 10 to the second, 10 to the third, and then again 10 to the 6th, 10 to the 9th, 10 to the 12th, and so on. So what are these called? 10 to the negative 15 is a femto. 10 to the negative 12 is a pico. 10 to the negative 9 is a nano. To the 6th is a micro. To the 3rd is a milli. And then centa. And then deca. Deca is 10 to the 1st. 10 to the 2nd would be hecto. 10 to the 3rd would be kilo. To the 6th is mega. To the 9th is giga, as in a gigabyte. And 10 to the 12th is a tera, as in a terabyte. This is big T, this is big G, this is big M. Then we have K, H, DA, D, C, little m, micro is mu, nano is N, pico is P, and femto is F. So now, how do I put scientific notation on my graphing calculator? If you look at the TI-83, you should see, I'm trying to picture it in my head here where it's at. It is in the second function. I think it's a period. The second function above the period, it's EE on your calculator. Capital E, capital E. In other words, if I wanted to take 2.6 times 10 to the 3rd and put it on my calculator, I would literally have to put in 2.6 second, whatever that button is, basically EE, and then enter 3. And that will give me 2.6 times 10 to the 3rd. Now it's not going to do an X because X is a variable. So how does it look in scientific calculation notation on your calculator? And then how to write on it. Write it on my paper. Well, scientific notation in your calculator doesn't do EE. It would do more like 2.6 E3. This right here is the scientific notation. This right here is times 10, and this right here goes there. Okay? All right. How do I convert units? How do I convert 1 day to seconds? Well, we do this. You've done this before. You did this in physical science. You did it in chemistry a lot, I'm sure. We start with the 1 day here. And then we start going, okay, so in 1 day, how do I get to that conversion? I'm going to do 24 hours. Do it the long way for once. Notice days and days goes away. And that's what you want. So now we need 1 hour down here, which is 60 seconds. Hours is gone. And then I'm sorry, 1 hour is 16 minutes. I knew something was weird there. 1 minute equals 60 seconds. So now, what we should get, we should know this, 86,400 seconds. How about 92 feet per minute to meters per second? 92 feet per minute. Feet. We want to go from feet to meters. We can go from feet to inches. Actually, we could go from feet straight to meters, couldn't we? We've got that. 0.3048. So 1 foot. Sorry. 0.3048. Oh. And now we got to get rid of minutes by saying 1 minute is equal to 60 seconds. We're going to take this and multiply across the top, divide across the bottom, and we end up with 28.04 meters per second. Okay? That is how you do. I think it'll be easy enough to tell. What we're trying to go through is from meters to micrometers. So if we're in here at meters, which would be right here, then 1, 2, 3, 10 to the negative 6. 10 to the negative 6. So that's what's... So now, you try a couple of these. First thing I need you to notice is we've got this in terms of two different things. We don't need to do that. We need to put it in terms of, say, minutes, because that would be easier. So 6 hours is going to be what? 6 times 60, so this will be 360 minutes. Plus the 40 minutes gives me a grand total of 400 minutes. Let's remember that, okay? Distance, meters per second. .5420 kilometers. 1 kilometer is 1,000 meters. And then minutes. And then 1 minute is 60 seconds. And I see where we're going here. Got minutes and minutes gone. Got kilometers and kilometers gone. We're just left with meters per second. And that leaves me with a grand total of 225.83 meters per second. And that would be the answer. All right. How can you do 15 centimeters per month and get it in terms of meters per second? Ooh, I have a feeling that one's going to be a small one. All right, so hopefully you tried this, and you should have gotten 6.0 times 10 to the negative 8 meters per second, 1.7 times 10 to the negative 11 micrometers, let's see, and then 12 times 10 to the negative 6 kilograms. Now, you want to see an easy way to do this, at least for the metric system part of it, it's pretty simple. So let's do this one. We start with 15 centimeters per month. 1 month is 30 days. 1 day is 86,400 seconds. And then finally, so days, days, months, months, centimeters. There are 100 centimeters in 1 meter. So now we have centimeters and centimeters gone, and we're left in meters per second. As you can tell, we've got meters here and seconds down here. So we are correct, meters per second. All right. These are really simple. To go from meters to micrometers, you know it's going to be getting even smaller. So let's look at our on there, guys. So if we take this and we start with 1.7 times 10 to the negative fifth meters, and we want to change that, then we're going to have to do what? And if we say 1 meter is equal to 10 to the 6th, what? Makes sense, there's going to be more of them. Sorry guys, sleepy apparently. So let's look at this guy. It says we've got 2 millimeter thick outer layer of the brain called the cerebral cortex. The cortex is spread out to cover roughly 1 meter squared. And then they said, okay, if you spread that out, you get an area roughly of 1 meter squared. Now we want to look at the cortex, and we find between 120,000 and 3,200,000 neurons per square centimeter. So we need to change this first to square centimeters. So if we have 1 meter squared, that is equal to 1 meter quantity squared, which means what exactly? 1 meter is 100 centimeters, so we're going to have to square this whole thing for it to disappear. So that's going to be 10,000 centimeters squared, because that's going to go away. Now, we are going to calculate about what we think. We're going to go with the lower amount, which is 120,000. So now we're taking 120,000 of them. Let's go ahead and make this 1, 2, 3, 4, 5. Let's make this 1.2 times 10 to the 5th. And we know that if we take that and we multiply it by the number of brain cells or neurons per square centimeter, that's what we're going to end up doing, is doing it times this. And we get 1.2 times 10 to the 9th power. Okay, that's 5 here. Oh no, 10. Excuse me, I miscounted. I don't know why I said 9. All right, so what do we have? 5 here. This is 10 to the 5th here business. So 10 to the 10th. Okay, that's how many neurons that were present. I want you to try number 2 on your own. Let's talk about the answer. This should be 642.22 light years. I will give you the answers to them though, so you can double check yourself. This guy ends up being 1 light year equal to 1.6646 times 10 to the 16th meters per year. And what's the distance for Earth to Betelgeuse? Well, that turns out to be 1.6646 times 10 to the 16th meters. In other words, it's a long way. What is relative error? It is the ratio of absolute error to expected value. Now, you all know this. Percent error would be delta x over x, and that is equal to x measured minus x expected divided by x accepted. And then turn it into a percentage, we have to put 100% on it. Okay, multiply by 100%. So how does this work? What is my percent error here? Percent error is delta x over x. So this is going to be, the x they measured would be 0.32. It's actually 0.34. And then multiply by 100, and we get, turns out, negative 5.88 times 10 to the second. In other words, percent-wise. All right. Now, I expect the length of your foot to be 16.2 centimeters. Oh, excuse me. It is actually 16.3. What was your percent error? Well, let's see. All right. Last but not least, significant digits. Whew. The good thing about AP physics is that significant digits don't really matter. Okay? In other words, anywhere from usually 2 to 4 digits are acceptable. So keep it down around there. So it says, why do we use it? Well, we use it to see if we solve correctly. And how do we use it? Well, the thing we really know is that dimensions are balanced. In other words, dimensions have to be equal. Both sides have to be the same result. So let's look at how we do this. It said verify that a equals v squared over r. Well, a is acceleration, which is meters per second squared. Velocity is meters per second, but the whole thing right here is squared, and then it's divided by r, which is meters again. So what we're looking to see is, do the same sides end up the same? In other words, this guy goes in. Good. That's m squared. No, that's m in the bottom. So this and this are going to go away. And so what you end up with is, you end up with a meters on the top you end up with second squared on the bottom, and look, both sides are the same here and here. So we know that is verified. So now, question number 2 says, which of the following could be correct based on dimensional analysis? So what they're asking you is to read and figure out what the dimensions are we're talking about. Flow rate, volume flow rate. Well, what is volume? Volume flow rate would be per second, so we're looking at volume over time. Well, what is volume? Volume is meters cubed. Time is seconds. So yes, that's a possibility. So this one is good. Let's look at the next ones. The height of the Transamerican Pyramid. Well, let's look at that guy. Is that one going to be correct? Height is just meters. Height is just meters, but this is meters squared, so this one is a no, it's not. Time required for a fortnight. Time is just seconds. This is meters per second, so that's also not correct. Speed of a train. Well, speed, velocity, is equal to distance over time. Well, distance is meters, time is seconds. Well, this is seconds squared, so no. Density. Well, density, this is density, equals volume divided by mass. Well, volume is, I'm sorry, that's backwards. Oops, excuse me. It's late. Let me get this done. Density is mass divided by volume. Well, mass is kilograms, so that matches, but volume is meters cubed, so that does not match. So again, this one's no. So the answer to this first one is A, isn't it? All right, so let's look at this last one. It says a block of mass M oscillates back and forth on the end of a spring, and it says you'll find that time t that the block takes for one full back and forth cycle depends on the constant k that has dimensions of mass divided by time squared. It says, according to this equation. So this is the equation we're going to be using. It says, use dimensional analysis to determine whether this result could be correct. So we want to see if that mass divided by time squared, so we're looking at mass is kilograms, time squared is seconds squared. So we want to see if K actually is that. Would that work to make both sides be equal? So we're going to start with T equals 2 pi, that's unitless, over m divided by square root of m divided by k. So we're going to put seconds over here, and we're going to check and see if our units are right. Square root of mass is kilograms. K, it says, is what? Kilograms per second squared. All right, well, let's look and see. Kilograms per second squared, that would be 2 pi square root of kilograms, and we know that dividing by a fraction is the same as multiplying by its reciprocal, so we got s squared over k kilograms. Well, those are going to go away. So we have s equals 2 pi times the square root of s squared. Well, square root and square go away, so this ends up being s equals 2 pi times s. So 2 pi is unitless, so our actual dimensions, units, are seconds. So yeah, the two sides are the same. So whether this result could be correct, the answer is, since the units match, on both sides, the results could be correct. Notice I'm actually writing this as a sentence. That's a good habit to get into with AP Physics 1. When you're answering correct questions, notice that this is my quantitative, and this is my drawing a conclusion and stating it. This is my qualitative. Okay, so when we look at those types of problems, and that's a big score free response on the Physics 1 test, is quantitative, qualitative. This is how we do that sort of thing. We're using the math to help us quantitatively, but we're also explaining qualitatively what that means. In other words, we understand that the conceptual part is that the units match on both sides. All right, that's the qualitative part. And then we're using that to justify the results could be correct. All right, guys, this is the end of lecture 1. You need to do homework problems. Your homework problems are right here. You have the paper, so go ahead and get those done, and I will see you on Wednesday. Again, I apologize for having to be out. Bye, guys. Be good.